Okay, for the next question, number 4, Nuclide X can decay by two routes. In route 1, alpha decay is followed by beta minus decay. In route 2, beta minus decay is followed by alpha decay. P and R are the intermediate products of Q and S, are the intermediate products, and Q and S are the final products. So to see what's happening, we have the following over here. Okay, so route 1, this is what happens. X undergoes alpha decay, intermediate products, and then you have the second type of decay. So there are two routes that this is going to take. Which among the statements are correct? Okay, and then we have our choices here. So to figure out what's going on, we are first going to label, okay, our atomic numbers and our number of protons. Okay, so X here, okay, we can just label A and Z for the number of protons that it has. All right. Now, if it, or the same thing here, okay, you're starting off the same way. Now, if it goes through an alpha decay, what happens to the number of, or the nucleon number? You're going to reduce that by 4. Okay, and if you don't remember or recall that whenever you undergo alpha decay, one of the products will be your alpha particle, okay, which is either denoted by alpha 42 or helium, okay, in particular 42. So this is the alpha particle as a result of the decay. Hence, if I started off with a certain nucleon number, if I undergo alpha decay, I'm going to reduce, okay, the atomic mass by 4. Okay, so this is going to be A minus 4, whatever that atomic mass is. And in terms of my number of protons, that is also going to reduce by 2. So I can write Z minus 2 here. So by the time it is at P as the intermediate product, the atomic mass has reduced by 4 and the number of protons has reduced by 2. Now we don't stop here because it will still go through negative beta decay once more. And recall that when you have negative beta decay, and I'm pulling this example right from your books, okay, an example provided, so this is for negative beta, okay, here. So we have thorium 23190. If it undergoes negative beta, the product will be this, which is protactinium, okay, and then 91, and then you have the negative beta particle plus an anti-neutrino. Okay, so what do you notice? If it undergoes negative beta decay, the product will actually increase by 1. Okay, this is what you're starting with. Your negative beta decay is negative 1, so the other product will actually be plus 1 so that it balances. Okay, so here if you look at this one, the negative beta particle, the atomic number or the atomic mass does not actually change. Okay, so this is going to remain as A minus 4 by the time it reaches Q. What will change, however, is your number of protons. So you're going to subtract 1 from that. Okay, so this is going to become Z minus 1. Okay, because you're starting with minus 2, okay, and then you're going to undergo the process, so you should end up with Z minus 1. Okay, so please don't get confused there. Alright, so that is for this first route. For the second route, okay, so it undergoes beta minus decay, so your A here will remain the same. Okay, because notice that that's 0 for beta minus. However, your number of protons will increase by 1. Okay, so it's kind of the opposite of what it seems to be. Okay, you're actually getting 1 here because this is the product side, remember? So if you have the beta particle which has negative 1, then the other result must be plus 1 so that it's going to balance out, if that makes sense. Okay, but anyway, this is what we have at this point, and then here it will undergo alpha decay, so this is going to be A minus 4. Okay, starting here it loses 4, and then your number of protons will now become Z minus 1. Okay? Because 1 minus 2, remember, if it's alpha, there's 2 there, is minus 1. Alright? So now that we've set this up, we can actually compare or check which ones are correct. So here, letter A. Q and S are different isotopes of the same element. So Q is here, S is here. Okay? They are different isotopes of the same element. They're not. They're actually identical. Right? Z minus 1, A minus 4, they're exactly the same. So they're not isotopes. So that is not correct. The mass numbers of X and R are the same. We can see that because the mass number A for X, okay, and R also has a mass number A. So they're the same, therefore, it makes sense that our answer is B. But let's verify letter C and D. The atomic numbers of P and R are the same. Atomic number of P and R are clearly different. This is A minus 4. This is A. Okay? And X and R are different isotopes of the same element. Okay? X and R, where are you? So X and R, no. Because in order for them to be isotope, the number of protons must be the same. Here, this is Z plus 1. So, this is not also correct. Therefore, the answer must be letter B. Okay, so I think what's confusing here is identifying the number of protons that are left. Remember, you are decaying, okay? This is your product. You're going to undergo, in this case, at least alpha and beta minus decay. Okay, if you're confused whether you're supposed to plus or minus, the particle involved here is the negative beta particle. Okay, and in the negative beta particle, like in this example here from the book, this is what you're beginning with. Okay, the daughter nucleus, which is the product, will have to have plus 1 the original number of protons because the negative beta decay has a negative 1. So if you balance that out, for example here, 91 minus 1, it should yield the original one that you have. So you're going to use that reasoning when you're doing a problem like this. Am I supposed to plus or minus? Well, it depends. Am I looking at the reactant or am I looking at the product? Okay, so there, okay, just remember, you start with Z, you're undergoing alpha decay, so minus 1, and then, minus 2, sorry, and then you undergo negative beta decay again. Okay, so what happens here is I'm going to plus 1 here, negative 2 plus 1. Even though this is negative 1, look at this part. Okay, you're looking at the daughter nucleus. So you plus 1, so this is going to become Z minus 1. Okay, and then here, same thing, negative beta decay, so plus 1, same reasoning we used. So we have Z plus 1, but then it goes to alpha decay. So alpha decay, okay, you have to subtract 2, so 1 minus 2 is Z minus 1. Okay, so I think this would be the most challenging part, but after you get used to this, recalling the definition of negative beta decay, then we should be able to get to the right answer. So hope this helps.